In this section, we are going to discuss the important meteorological variables that forecasters need to understand when developing an air quality prediction. These include temperature, pressure, and water vapor. These are important variables because they define the state of the atmosphere, they are predicted by all weather models, and they directly or indirectly affect chemical reactions, emissions, dispersion, transport, and deposition of pollutants. As forecasters, we need to look at different formulations of these variables because they help predict different weather phenomena, which we will cover in later sections of this training course. Let's start with temperature. Temperature is an important variable that affects PM 2.5 formation, emissions, dispersion, and transport. At lower temperatures, there is more home heating, which will increase the primary PM 2.5 emitted into the atmosphere through residential wood burning. While at higher temperatures, there's increased volatilization of VOCs and increased biogenic emissions. So temperature can go either way when you're looking at the impact on pollution. Forecasters are interested in changes in temperature in the vertical direction, such as looking at temperature inversions, in the spatial direction, such as looking for the presence of a warm front or a cold front, and temporally to evaluate how mixing heights will change throughout the day. Now, there are two processes that can cause changes in temperature, which we will discuss next, and these are convection and radiation. So let's begin with convection. Convection is vertical heat transfer by mass movement, and this is something that occurs naturally in the atmosphere. Everybody has heard the phrase hot air rises. Well, this is the process of convection that happens every afternoon as you get uneven daytime heating of the ground. You get these air thermals that will start to rise like a warm air bubble rising up in the atmosphere, and that is physically moving heat from the ground to a different part of the atmosphere. So that is the process of convection in the vertical direction. Now, if we were to look at the horizontal transfer of warm air, that would be what we call advection. Advection can be identified by looking at temperatures upwind and downwind of a given location. If you have colder air upwind moving into a region of warmer air, that is cold air advection. And this is actually what happens when a cold front moves through a given location. You are replacing a warmer air mass with colder air. On the other hand, if you have warmer air upwind moving into a region with colder air, this is warm air advection. And this is what happens when a warm front moves through a region. Now, the stronger the wind speeds that you have, or the greater the rate of the horizontal temperature change, you're going to have stronger temperature advection. As we look at this graphic, we can see examples of warm air advection and cold air advection denoted by the circled areas. The color contours on this map represent temperature, while the wind barbs overlaid on top of the color contours tell us what direction the air is moving. In the area circled for warm air advection, we can see that the wind is coming out of the southwest, transporting warmer temperatures towards the northeast. If we move to the area of the graphic where we see the cold air advection highlighted, we see northwesterly wind blowing, which is transporting colder air from the northwest toward the southeast. Now that we've talked about convection and advection and how that changes temperature, let's talk about radiation. As we know, the sun radiates energy towards the earth all the time when we can see the sun. That's what causes us to get sunburned during the day, but it also causes the earth to heat up. The balance of incoming and outgoing solar radiation is a critical component of diurnal temperature changes. The earth is constantly emitting energy, seen here as outgoing earth energy. During the daytime, the sun supplies incoming solar energy to the Earth's surface. The maximum incoming solar energy occurs at around noon each day, when the sun is most directly overhead. However, the Earth continues to warm through much of the afternoon, while the incoming solar energy exceeds the outgoing energy from the Earth's surface. At about 3 p.m. each day, the amount of incoming and outgoing energy are equal. At this time, the energy at the Earth's surface has reached its net peak for the day, and the maximum daily temperature is reached. From this time until just after sunrise the next day, the outgoing energy exceeds the incoming energy. During this period, the Earth is continually losing energy and cooling. As a result, the minimum temperature occurs just after sunrise when the incoming and outgoing energy are equal and the Earth stops cooling. So if we look at this example of some time series plots for a sunny day and a cloudy day, we can clearly see the impact of the amount of solar radiation on the temperatures. On the sunny day, which is shown in the top graphic, we see a definite peak in the temperature in the early to mid-afternoon, whereas on the cloudy day, the temperature remains fairly constant throughout the whole day, because we do not have that strong incoming solar radiation changing the temperature as rapidly as we do on a sunny day. So where do we get temperature information? This graphic that you see now is showing the standard station plot that you can get from a variety of sources on the internet, and this is the standard format for transmitting weather information in a graphic display. The temperature data, as highlighted on this graphic, is always going to appear on the upper left-hand corner of the plot. I know there's a lot of information shown here right now, but as we work our way through the meteorological sections here, we will cover all the different variables that you see. So by the end of this course, you'll have a better understanding of the other weather phenomena that you can get from these surface observations. Now, if we look at an example of this same type of plot in a more spatial view, which is more realistic to what you would see as a forecaster, you can see that we have several stations' data plotted all in this area. This is for the Seattle region. And the temperature is always going to be the upper left-hand corner number. So throughout all of these stations here, you can see they all have a temperature value reported. So you can take a quick look spatially and see how the temperature is varying across a region. Okay, back at the beginning of this section, we mentioned that we need to also look at vertical temperature changes. We've covered the horizontal changes by looking at the data and explaining convection and advection and radiation, but let's look at the vertical temperature profile and see what we want to look for in that data as well. This schematic here shows the sort of standard temperature change throughout the atmosphere from the surface of the Earth all the way up into space. And what we're concerned about as forecasters is really the lowest 10 kilometers, which is defined as the troposphere. You can see that at the very bottom of the graphic here. And while temperature above the troposphere goes through different changes, gets warmer in some layers and cooler in other layers, in the troposphere itself, in general, the temperature cools as you go up in altitude. Now, if we look at an actual profile of temperature from a specific location, we can see that there's much more variation. It's not just a steady decrease in temperature as you go up in altitude, but we have lots of smaller scale changes where in some layers the temperature increases, in some layers it decreases. This is important for forecasting because you need to know how this is going to impact your vertical mixing. Is it going to trap your pollutants near the ground? Now, how do we get this data? Well, the temperature is measured vertically by twice daily weather balloons. Many of you have heard about weather balloons. They put an instrument pack on the bottom of a large helium balloon and launch it twice a day at about 150 locations across the US, and then the result of that balloon data can get plotted on a graph like this so we can evaluate those changes in the vertical direction. You can also measure temperature vertically through different remote sensing instruments and even through aircraft. As they take off and land at different airports, they can record the changes in temperature as they go through the different layers of the atmosphere. And again, as I mentioned, these vertical temperature profiles and how to interpret them in great detail will be covered in a later section of this talk. But for now, I just wanted to show you how you can see the changes in temperature just through the raw data at any given location.